Chapter 16 now, and we're going to talk about acids and bases. Okay. So this is basically an extension of chapter 8, the sections that we talked about in acid-base chemistry. Then, if you don't remember, you should probably go back and review the acid-base reaction, how to write molecular complete ionic and net ionic equations, and do any of the end of chapter problems that you're going to need to. Because again, I'm going to assume that you know how to do that since you've already had that course. So we're going to talk about different concepts of acid-base chemistry. And the first concept that was given was called the Arrhenius concept. And it was fairly limited, as we're going to see. It forced all reactions to occur basically in water. Then Bronsted-Lowry expanded that definition to basically call these acid-base reactions proton transfer reactions. And then finally, the Lewis concept, which encompassed all acid-base reactions, started looking at how lone pairs were being donated to form coordinate covalent bonds. And that's going to be the overwhelming definition of the Lewis acid-base concept. We're going to mainly use Bronsted-Lowry concept. But for those of you going on to organic chemistry, the Lewis concept is going to be the most important. Actually, you're going to use both the Bronsted-Lowry and the Lewis concept. So this is going to be really important in organic chemistry. We're going to focus on the Bronsted-Lowry concept, as we will talk about as we move on. Savant Arrhenius first came up with this idea about what an acid was and what a base was and what acid-base reactions were. And basically, he simply said that an acid is a substance that when you put it in water, increases the hydrogen ion concentration. Okay, and a base then was simply something that when you dissolved it in water, it increased the hydroxide ion concentration. So it was very specific. You had to put it in water, and an acid increased the hydrogen ion concentration, which we're going to call our acid. I'm going to call that hydrogen ion the acidic proton. Okay, now it is an acidic proton because, remember, a hydrogen ion has a single proton and a single electron. And when you lose the electron, you have H+, which means it's nothing more than a proton. Okay, so we're going to often refer to that as the acidic proton. So the acidic proton is nothing more than a hydrogen ion. Okay, now the hydrogen ion itself, again, this is just a proton. It doesn't actually exist in solution. Okay, it has a very high charge density. So since it's so small and it has a full +1 charge, it really attracts the polar molecules that are around it. In fact, it attracts it so much that it actually forms a bond, a chemical bond, to form the hydronium ion, H3O+. So keep in mind that H+ does not exist in water, ever. It always exists as H3O+. However, we're oftentimes just going to write it as H+, and understanding that that H+ really is going to form H3O. It's going to simply react with one of the solvent water molecules and form the hydronium ion. Okay? So again, we're oftentimes just going to use H+ rather than use H3O+. Now, the aqueous means the same thing it did for the salts. You know, when we talked about ions being in solution, the aqueous again simply means that there's a bunch of water molecules that are coordinated around the ion. In this case, this is a positively charged ion, but again, the positive of a water, the positive hydrogen part of the water molecule is going to be attracted to the negative portion of the oxygen. And again, you can see that we have what is called the hydration shell. And there's many more water molecules that actually surround this. And then there's second shells and third shells all around this. Now, the shells get weaker and weaker and less ordered as you move out. But again, this is basically what we mean by aqueous, is that the ions are actually being solvated. This is why the ions easily dissolve within the solution. Okay. So strong electrolytes completely dissociate. Now, as you recall, we talked about this. The reason they're dissociating is we're replacing those strong ionic chemical bonds with a whole bunch of these ion dipole interactions. And the sum of all these ion dipole interactions, if the sum of all these ion dipole interactions are greater than the ionic bond strength, then the salt will readily dissolve, right? And we formed, and we called that a strong electrolyte. So the salt completely dissociated, right? And we called that a strong electrolyte. Well, the same thing is going to be true with acids and bases. If they fully dissociate, we're going to call them a strong electrolyte. And if they only partially dissociate, we're going to call them weak electrolytes. So roughly speaking, again, strong electrolytes, which were soluble salts, are considered to simply have an equilibrium constant that's greater than 1, okay? Again, this isn't a steadfast rule. This is just an approximation. We'll find that things that we consider to be soluble, some of them might be a little less than 1, but still close to 1, okay? So just to give you an idea of why we say that, let's talk about the percent dissociation for a 0.1 molar solution of any of these soluble salts, okay? Basically, if you have an equilibrium constant value, so a K value, and then here will be the percent dissociation. So if we have a 0.01, so that's 10 to the negative 2, the percent dissociation, whoops, this is out. Wow, this is all messed up. Okay, so if we have again, a K value like 10 to the negative 2, only about 27% of it dissociates. If we go up to a 0.1, we're at 62% of all the ions actually dissociate. And once you get to 1, 92% of all of the ions in that salt have dissociated. And then again, that remaining 8% just remains as a solid chunk at the bottom of your beaker. And once you get to 10, we're already up to 99%. So again, you can see why when we say 1, approximately 1, basically nearly all of the molecules or the ionic compounds have dissociated into their individual ions. If it's less than that, we call it a weak electrolyte, right? If it's 10 to the negative 2, only 27%. But we're going to deal with things that are 10 to the negative 33. Which means that basically almost very, very, very little of it actually dissociated. So again, this is just roughly saying that when a K value is around greater than 1, we generally say that it's a strong electrolyte. Now, in the Arrhenius concept, a strong acid is simply a substance that completely ionizes to give up the hydrogen ion or the hydronium ion and whatever the counter anion was of that particular acid. So completely dissociate. So for example, we have nitric acid. As you know, nitric acid is one of our 6 strong acids. And again, it's going to fully dissociate. It's going to dissociate into H plus and NO3 minus. But again, we know that the H plus really doesn't exist. It exists as H3O plus. We're going to find out later that it's often better for understanding that we actually write it like this. Not that it just simply dissociates, but that it is an exchange reaction. This guy is giving up its H plus to the H2O to form H3O plus, leaving behind the NO3 minus. So again, 100%, we draw a single arrow indicating that that is a strong electrolyte and it is going to products, okay? So how do you know if it's a strong acid or a weak acid? Well, it's quite simple. You need to know your 6 strong acids, which of course you learned in Chem 110. Okay, they're in the tables that you must know. And so we have the 3 binary acids, the hydrochloric, hydrobromic, and hydroiodic acids. And we have the oxo acids, nitric acid, perchloric acid, and sulfuric acid. There are a handful of other strong acids out there. In fact, there's some things that are called superacids. But again, the superacids are really rare, and there's very few other acids that we would consider to be strong. But these are the common acids, Okay, those other ones that I'm talking about, you probably will never see in your lifetime or even hear about in your lifetime. They're very rare. So these are the common acids and these are the strong acids. Okay. Strong base, again, very similar. So according to Arrhenius, we have to increase the hydroxide ion concentration. But it completely dissociates, okay, or ionizes, I should say. I won't want to use the word associate, but it ionizes to increase the hydroxide ion concentration. Now, we know that the sodium hydroxide, which is a solid out of water, when we throw it in water, will completely dissociate into the sodium ion and the hydroxide ion. Again, the hydroxide being our base. So when the hydroxide ion concentration is greater than the hydrogen ion concentration, we say the solution is basic. And vice versa, if the hydrogen or hydronium ion concentration is greater than the hydroxide ion concentration, we say the solution is acidic. Okay. So again, how do you know if it is a strong base? Well, again, you must know the 6 strong bases. These are in the tables that you must know, okay? And if you look at your periodic table, starting at group 1, you have lithium. And then as you go down that group, it goes lithium, sodium, potassium, and you simply move over a column and you end up with calcium, strontium, barium. And again, remember the calcium, strontium, and barium are in group 2. So they have 2 hydroxides. And both of these come off. They fully dissociate when you throw them in water. Okay, so both of them come off. We're going to find out that that's not true with the acids. So for example, sulfuric acid is a diprotic acid. But only the first acidic proton is strong. What's left behind is the HSO4 minus. That's a weak acid. Okay, so only the first one is strong. But in the case of the hydroxides, both of these come off, okay, for the strong bases. Okay, so now weak acids and bases do not completely ionize. In fact, a very small fraction of the molecules actually ionize, and that's why we don't show weak electrolytes, weak acids, is being dissociated when we go from the molecular equation to the complete ionic equation. The complete ionic equation, again, is really showing what's really existing in solution. And so in the case of weak electrolytes, a very small portion of them dissociate and the vast majority of the substance is still intact. And that's why we don't show it as being dissociated in the complete ionic equation, because very little of it actually dissociates. So again, the vast majority of acids and bases are weak. Again, how do you know they're strong? Well, if it's not one of the 6 strong acids, it's a weak acid. If it's not one of the 6 strong bases, it's a weak base. Okay, again, it's that simple, don't make it hard. So acetic acid is an example. So this is simply vinegar. Acetic acid is a solution of the acetate with a hydrogen on it in water. And when you throw that in water, the hydrogen ion is transferred to the water to form the hydronium ion. Now, we could have also wrote this as simply H plus and eliminated the water out of this reaction and showed this as dissociating as H plus and then the acetate, the C2H3O2 minus. But as I'm going to show you here in a little while, very, very little of acetic acid actually dissociates to form the hydronium ion and the acetate ion. Another example of a weak base is ammonia. Now, if you go online, you're going to find that some people say that ammonia is not an Arrhenius base, and then you're going to have others that say ammonia is an Arrhenius base. It doesn't matter. It's irrelevant. If you actually read the papers of Arrhenius on this subject, he simply says that any substance that you dissolve in water that produces the hydroxide ion would be considered an Arrhenius base. Some people say that it has to dissociate to form the Arrhenius base, but if you actually read his papers, it doesn't. It just simply says, it uses the word produces. Now, what he really meant, well, he's long gone, so we don't know. But from what he wrote, we would consider any substance that when dissolved in water that increases the hydroxide ion concentration would be considered to be an Arrhenius base. Okay, again, totally irrelevant unless you've actually heard of this argument. It doesn't really matter. Okay, next, I want to say that the Arrhenius concept is extremely limited because it's saying that you can only have acid-base reactions in water. And that's just not the case. So that's when two different, one chemist, one physicist came along, and they actually published separately. They weren't collaborating. They published separately, but they published at the same time. And they both came up with this idea that, well, Arrhenius is too limited because we know that acid-base reactions can occur in other solvents rather than just water. Okay, so water is what we consider a protic solvent. So it was able to either donate or accept a proton. But acid-base reactions aren't dependent on the water itself. And so Bronsted-Lowry came up with this concept that an acid is simply a proton donor. So it's a proton transfer reaction. So an acid simply gives up H+. And they said a Bronsted-Lowry base is just whatever accepts that proton. So they eliminated the hydroxide out of the whole picture. Okay, and we're going to find out that that's a good concept because we're going to find out that neutral nitrogen-containing molecules can act as bases. Okay, now they may produce hydroxide if they react with water, but they don't necessarily have to. Okay, so a base then was simply the proton acceptor. The acid was the proton donor. So let me show you. So here's an example. We have ammonia reacting with water to produce the ammonium ion and the hydroxide ion. So this is the net ionic equation, right? A molecular equation wouldn't have any ions in it. And a complete ionic equation, this is actually both a complete ionic equation and a net ionic equation. But remember, the net ionic equation wouldn't have any spectator ions. So this is the net ionic equation. And basically what you can see is that the the water, I thought I fixed all of these, but I guess not. So the water is giving up a hydrogen ion to ammonia. So there's a lone pair on this nitrogen, as we're going to find out later on. And it is forming a coordinate covalent bond. So the hydrogen ion is forming a coordinate covalent bond with the nitrogen to form the ammonium ion. So in this case, we can see that water is the acid. Since it's the proton donor, water is the acid. And since the ammonia is the proton acceptor, it must be the base. Okay, so this is the, and this is the Bronsted-Lowry concept of acids and bases. This is the one that we are going to use for the most part throughout this course. On occasion, we'll talk about Lewis acids, which we're going to talk about here shortly. But again, this is the one you really need to concentrate on. This is the acid-base concept that we're going to use basically throughout this course. Okay, so again, water donated the proton, so it's the acid, and the ammonia accepted the proton, therefore it is the base. Now, if we look at the reverse reaction, right? So remember, we're now going in this reaction. Remember, this is equilibrium, so it goes this way and it goes this way. They just go at the same speed, so it looks like the concentrations of the reactants and products aren't changing. But remember, these reactions are dynamic. So what's happening is that the ammonium ion is now giving up a proton to the hydroxide. So in this case now, the ammonium ion is acting as the Bronsted-Lowry acid, and the hydroxide, which is accepting the proton to form water, is going to be the Bronsted-Lowry base. Okay. Okay, so again, we see that the species NH4 plus is acting as an acid, and the NH3 is acting as the base. Well, we call this a conjugate acid-base pair. The only difference, this is really important, you might want to write it down. The only difference between a conjugate acid-base pair is H+. If you go from a conjugate, if you go from a base to form its conjugate acid, you add H+. If you go from an acid and you want its conjugate base, you subtract H plus. It is literally that simple, okay? Now you're going to see some molecules along the way where you're going to want to do other things. Don't, okay? Again, it is just a difference in H plus. So the lingo would be is that NH4 plus is the conjugate acid of NH3, or you could say that NH3 is the conjugate base of NH4. Okay, so these are conjugate acid-base pairs. Now, is there another conjugate acid-base pair? Does anybody see yet another conjugate acid-base pair in this reaction?
Hydrogen and the hydroxide.
Hydrogen?
H2O and OH.
Yeah, right. So this is the other conjugate acid-base pair, right? Is water the acid or the base?
The acid.
Yeah, it's the acid, right? It has one more H than the base does, right? Again, that's the only difference between an acid-base conjugate pair is H plus. So when I add H plus to the base, I get H2, and then the plus and the minus cancel, which gives us the neutral water molecule. So yeah, there's our other acid-base conjugate pair. So oftentimes, not always, but oftentimes a acid-base neutralization reaction like we're showing here oftentimes has two sets of conjugate acid-base pairs. Again, like I said, not always, and we'll see those examples where they don't, but most of the times there are two sets of acid-base conjugate pairs in an acid-base neutralization reaction. Okay, next I want to talk about amphoteric species. So these are molecules that can either act as acids or bases. Now this is going to be an important definition in organic chemistry, amphoteric. But we're going to specify one type of amphoteric species, and we're going to call it amphiprotic. We'll actually talk about amphoteric again later on in coming chapters. But for right now, we're going to concentrate on a subtype, which is amphiprotic. So in this case, an amphiprotic species can either accept or donate H plus. This is more broad, simply saying that the molecule can act as an acid or a base, which is going to include that Lewis acid-base concept. This is basically just for the Bronsted-Lowry concept, amphiprotic. So again, it's a molecule that either can accept or donate H plus. Here's an example. So here's the bicarbonate ion, right? So this is baking soda, sodium bicarbonate. So this is why when you have either an acid spill or a base spill, you always pour the same thing on it. You pour sodium baking soda on it, sodium bicarbonate, because it can act as either a base or an acid. In this case, let's say that we have a base spill and we have a hydroxide and we want to neutralize it. Well, we just throw on the sodium bicarbonate, the baking soda, and the hydrogen ion is going to be given up to the hydroxide to form water, and then all you leave behind is the carbonate. So in this case, we can see that the H plus is being donated from the carbonate to the oxygen, right? So this loses H plus, so it becomes CO3, and then we lost a plus, so this becomes -2. This gained H plus, so it's going to become H2O, and then the plus and the minus cancel to give us the neutral water. Okay, so here we can see that it's acting as an acid because it's donating a proton. But if we have an acid spill where we have an excess concentration of H plus, well, in this case, the sodium bicarbonate is going to actually accept the H plus. So in this case, then this is the acid, and this is acting as a base since it's accepting H plus. The H plus, of course, now we're going to have two of them, so it'll be H2, and the minus and the plus cancel, giving us a neutral carbonic acid. And as if you recall, carbonic acid is unstable, and what happens to it? Have any of you ever made volcanoes in school where you mixed baking soda and vinegar? So as you recall, again, from Chem 110, you need to go back and review this stuff. Any salt that contains a carbonate that reacts with an acid initially forms carbonic acid, but it's unstable and breaks down into water and carbon dioxide gas. So that's what makes the volcanoes. It's forming carbon dioxide gas, and then it just bubbles everywhere out of solution. Okay. So again, but in this case, again, we can see that this time it's acting as a base since it's accepting H plus. So now it's accepting H plus, and so therefore it's a base. So this is an amphiprotic species. It can either accept or donate a proton. So it can either act as a base or an acid. So water is a very important amphiprotic compound, okay? And we're going to actually use it to quantify all of our other acid-base reactions, all of them that occur in water, okay? So here's an example. We have ammonia. When it's thrown in water, the water will give up a proton to the nitrogen, again, that lone pair on the nitrogen. So it's giving up H plus, so it's going to be NH4 and then the plus, so NH4 plus. And then this just lost H plus, so it's now just OH, and we lost a plus, which means there must be an overall minus charge. So here again, we can see that the water in this case is acting as an acid because it's donating H plus. But if I put an acid in water, okay, well, we know that the hydrofluoric acid is going to donate a proton to the water, leaving behind F minus. And again, we just added H plus to H2O, so it's going to be H3O and then plus, so our H3O plus, our hydronium ion, okay? Now, this is where it would be, so in this case, we can see that it's acting as a base since it's accepting the proton. So this is, a lot of times we would write this simply as HF goes to H plus plus F minus, and it would be difficult to see these acid-base conjugate pairs, right? Here's one acid-base conjugate pair, here's the other acid-base conjugate pair. That's why a lot of times it's better or easier if you always just show the water in an acid reaction forming the H3O plus, okay? I will do it most of the time, but on occasion, I will just write H plus. I do that because in real life, there's going to be a lot of people who simply write H plus and they don't write the hydronium line. You need to be able to recognize that that's what it is, okay? Okay, so now in the Bronsted-Lowry concept, we said a base is simply a species that accepts proton. OH minus is only one example of a base. So this is, again, the benefit over the Arrhenius definition. Acids and bases can be ions as well as molecular substances. So we know that carboxylic acids, which are neutral organic molecules, can actually become ionic, become an acid and donate H plus. Same thing with nitrogen, neutral nitrogen containing molecules. They can actually accept H plus and form and become ionic and form an ion, okay? Acid-base reactions are not restricted to aqueous solutions, so water doesn't need to be involved anymore. It can be in the gas phase. It can be in any other solvent, okay? So again, we eliminated the fact that it has to be in water. Some species can either act as acids or bases. Again, we've seen that with the bicarbonate ion, we've seen it with water, and we'll see it in many other species as we go along. Now, many acid-base reactions do not involve the transfer of hydrogen ions, okay? Again, particularly, again, you're going to see this in organic chemistry. Most chemical reactions that occur are Lewis acid-base reactions. So in organic chemistry, the vast majority of chemical reactions you're going to talk about would be considered to be Lewis acid-base reactions, okay? So this concept was developed by Gilbert Lewis, and basically he said that an acid is simply a substance that accepts an electron pair to form a coordinate covalent bond. And a Lewis base is simply a substance that has that lone pair, okay, to donate to form a coordinate covalent bond. So very simply we say a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. So this is the lone pair that it's donating to form a coordinate covalent bond. The acid, again, accepts that pair of electrons to form a coordinate covalent bond. So remember, a covalent bond is where you had an unpaired electron in one orbital of one atom and an unpaired electron in another orbital of another atom. Those two orbitals overlap to share that pair of electron, and we called that a covalent bond. A coordinate covalent bond, we have a pair of electrons on one atom and just an empty orbital in the other. The empty orbital overlaps with that pair of electrons in that orbital, and they form what's called a coordinate covalent bond. Okay? So here's an example. Here I have boron trichloride, and it's going to react with ammonia. Now you might say, well, okay, I already know ammonia is a base because I had to memorize that in Chem 110, right? But boron trichloride certainly does not look like any acid I've ever seen. It doesn't have H+. But what happens, boron trichloride will react with ammonia to form this compound here. And what happens is that the empty orbital, okay, there's an empty 2p orbital on this bromine, overlaps with the orbital containing the lone pair on nitrogen, and it forms this coordinate covalent bond. So this guy then is the electron pair acceptor, that would be our acid, and this would be the electron pair donor, and that would be our base. Okay, and again, we then form this coordinate covalent bond right here. Okay. The equations that you need to know for this chapter, and again, I suggest you memorize them because that's what you would normally do in class. And again, there's an extreme advantage to it. Again, I don't do it just to be mean or make the course more difficult. It helps students do better in the class. So we're talking about equilibrium. And so if we have some generic reaction, so we have A reacting with B in equilibrium to form some products, and again, it's products C and D. We have the balanced equation where the coefficients are represented by the lowercase letters for each of the reactants and products. So the equilibrium constant is going to be unique then, of course, to every different chemical reaction, and that's a capital K as opposed to the lowercase rate constant that we just studied in the last chapter. And it's just going to be the concentration of the products, each raised to the coefficient in a balanced chemical equation, divided by the concentration of the reactants, again, each raised to the coefficient in the balanced chemical equation. Now, of course, pure solids and pure liquids do not appear in the equilibrium constant expression, only gases and aqueous solutions. And so we've seen all that in the last chapter, but that's all going to apply to this chapter, and the next chapter again is going to be even more equilibrium stuff. So again, this stuff is all going to apply. So the more you know that first chapter, that chapter 15, the more you understand it, the much easier the next two chapters are going to be, because it's, again, just all equilibrium stuff. And now, instead of just using a regular K, we introduced Ka, which was the acid dissociation constant. We're going to talk here shortly about Kb, which is the base equilibrium constant. So we're going to call it Kb. We're going to learn today, no, we've already talked about this. We talked about the self-ionization of water, and it had an equilibrium constant expression that looked like this. So Kw, the equilibrium constant, and at 25 degrees Celsius, Kw was equal to 1.0 times 10 to the negative 14, okay? We know that the hydrogen ion concentration is going to be equal to the hydroxide ion concentration in pure water, And that's how we came up with this expression here. But we're going to be able to use this same expression if we have an acidic or basic solution. And from this expression, we'll be able to relate the hydrogen ion concentration to the hydroxide ion concentration. And we'll talk about that later on today. Then we talked about the negative log of the hydrogen ion concentration. So that's just what the P represents, the negative log. And then H simply represents the hydrogen ion concentration. And again, remember, we could replace H plus with H3O plus, because H plus really doesn't occur in nature. It only ever exists as H3O plus, okay? So, but the pH then is simply the negative log of the hydrogen ion concentration. And the only reason we do this is so that we don't have to deal with scientific notation, okay? We talked about what the pH means. We said for a neutral solution, the pH was 7. For an acidic solution where the hydrogen ion concentration is greater than the hydroxide ion concentration, it would have a pH less than 7. And for basic solutions in which the hydroxide ion concentration is greater than the hydrogen ion concentration, the pH is going to be greater than 7. We're also going to talk about the hydroxide ion concentration, and we're going to talk about it in terms of POH, which of course is just a negative log of the hydroxide ion concentration, okay? And then we're going to talk about the relationship between pH and POH at 25 degrees Celsius. And we're going to be able to say that the pH plus the POH is simply equal to 14. And again, that'll be at 25 degrees Celsius. We're going to talk about the degree of ionization. So in other words, how much does a ionic compound actually dissociate or react to form its ions? We call that the degree of ionization. We're just going to use an alpha as the variable to represent that. And basically that is simply going to be the concentration. And here, I'm just showing it as an acid, the degree of ionization for an acid, where the A minus is going to represent the conjugate base, okay, at equilibrium. So there's nothing written here. So when we write this, we're assuming equilibrium. And when we divide that by the initial concentration of the acid, so this is a naught, that gives us the degree of ionization. For percent ionization, just multiply that by 100%. So on an ice table, this is the initial acid, and this is the equilibrium conjugate base that's formed from the dissociation of that acid. We could do the same thing for any ionic compound. This would just be the initial of the undissociated compound. This would be the concentration of one of its constituents at equilibrium, okay? So this is just the reactant and the product. But again, initial and equilibrium. We're also going to talk about how we can, we don't have to use the quadratic formula all the time, because that would be a real pain in the butt, because all of these problems are going to end up requiring the quadratic formula. But we're going to see that we're going to be able to ignore it at certain times. We're going to accept a certain amount of error or uncertainty in our calculations. And we're going to use a ratio where we simply take the concentration of the acid and we divide, that's the initial concentration of the acid. So that's this guy here, okay? That's the initial concentration of the acid divided by its equilibrium constant. In this case, I'm talking about acids. Now, if that ratio is greater than 100, we're going to be able to ignore the minus X term and this will make more sense once I show you some examples of it, but we're going to be able to ignore the minus X term, which is going to allow us to not have to use the quadratic formula. And we're going to do the same thing for bases. So if we take the initial concentration of the base divided by the Kb, if that is greater than 100, again, we're going to be able to ignore the minus X term. Now, in the next chapter, we could do this for acids and bases. But in the next chapter, we're going to talk about solubility. We're going to be talking about complex ions. We're not going to be able to use this idea for them. This only works for acids and bases. Once we get to those other things, we will make other assumptions right off the bat, and then we're going to check and see if those assumptions were appropriate or not. So keep in mind that this will only work for acids and bases. And then finally, we're going to see that there's actually a relationship between the equilibrium constant for an acid and the equilibrium constant for its conjugate base. So if we have a conjugate acid-base pair, if we multiply those two things together, we're going to get Kw. And later on today, I'll explain why that is true. But these are all of the equations that you need to know for this chapter. So there's really not a lot of equations. They're not that hard. This guy, again, you've already know how to do this. This is going to be unique for every different chemical reaction. Okay, so let's try some examples. So it says, describe both the acid and base in terms of the following definitions, of course, Arrhenius, Bronsted-Lowry, and Lewis. So Arrhenius definition. So in this case, what is the Arrhenius acid and or base in this reaction? Taylor, what do you think the Arrhenius acid or base? So what is the definition, let's say, of an Arrhenius acid?
The acid is a proton donor.
Nope, that's a Bronsted-Lowry.
Oh. Is the H2O the acid?
But what is the definition of an Arrhenius acid?
An electron pair acceptor?
That's Lewis.
Oh, sorry, I'm like going through my notes. I'm not sure.
So an Arrhenius acid is a substance that when dissolved in water increases or produces the hydrogen ion, and a base is a substance that when dissolved in water generates the hydroxide ion. So do you see either an Arrhenius acid or Arrhenius base?
The H2O?
No.
I don't know.
So in this case, it's going to be NH3. Okay. So in this case, the NH3, and I believe the homework solutions, I say that NH3 is not, but I've been fighting with this for years until finally this year, I finally was able to get the original papers of Arrhenius. And again, from the wording that he uses, NH3 would be the base, because when ammonia is dissolved in water, it generates the hydroxide ion. However, there is no acid in this reaction, because when the acid's dissolved in water, it generates the hydrogen ion. But do you see any hydrogen ion over here? There isn't. So this is the problem with the Arrhenius definition. It was just way, way too simplified. Okay. So now we get to the Bronsted-Lowry. And so, Hannah, what is going to be the, what is the definition of a Bronsted-Lowry acid?
The Bronsted-Lowry acid is a proton donor.
It's a proton donor, and a base
Is the proton acceptor.
Okay, so what is the acid? What is the proton donor in this reaction?
The water.
Water, right? It's given up one of its hydrogen to the lone pair that's on this nitrogen to form the NH4, right? So it was NH3, we gained H plus, so this becomes NH4 and then the plus sign. And then this guy lost an H, so it's just going to be HO or OH. And because it gave up a plus, that means it has to have a minus left behind. Okay, so in this case, I could see that the water is the Bronsted-Lowry acid. And so Hannah, what's the base?
The NH3.
The NH3 then is going to be the base. Okay, then Lewis. So, Katrin, what is the definition of a Lewis acid?
A Lewis acid can
I can't hear you.
oh, it's
Still can't hear you. There we go.
I don't, it's not muted. I'm not sure.
Jada, what do you think?
The Lewis, isn't that when an accepts a electron?
Yeah, it accepts the electron pair, right? It
Oh, that
donates a proton for Bronsted-Lowry, but accepts an electron pair for the Lewis. And then what is the Lewis base?
The Lewis base will be would it be the water?
What did you just tell me a Lewis? What was the definition of a Lewis acid?
It accepts a proton.
No. That's Bronsted.
I mean electron. Sorry.
Yeah, right. It accepts a pair of electrons to form a coordinate covalent bond.
So it'd be the NH4. But yeah.
No, it has to be. We're talking about the reactants here, right? So what accepted a pair of electrons to form a bond?
The NH3.
The NH3 donated the pair of electrons. So
then
the hydrogen from the water, right?
mhm.
So that means that the water is the acid, right? It accepted the pair of electrons from the ammonia to make the coordinate covalent bond that's found in NH4 plus. Okay. So
Okay.
in other words, let me just write it, right? So we have here we have NH3, and this is the most probable structure. All the formal charges are 0, okay? And we see that it has a lone pair. And then the water looks like this. Now it too has lone pair, but we can see from the chemical reaction what happened. We can see that this hydrogen left behind the pair of electrons, right? So this left is H plus. And then we now have this. Where this has a +1 formal charge and this has a -1 formal charge, thus the charges on the ions. And so that coordinate covalent bond was formed right here, right? This would have been the coordinate covalent bond. So now we can see that the water accepted the lone pair to form the coordinate covalent bond, and it was the ammonia that donated it. So therefore the ammonia is the Lewis base. And really they should, all three theories should be consistent, because the Bronsted-Lowry theory encompasses the Arrhenius theory, and the Lewis theory actually encompasses both of those as well. So these should always, a Lewis acid is going to be a Bronsted-Lowry acid, or I should go the other way. An Arrhenius base is always going to be a Bronsted-Lowry base, is always going to be a Lewis base. It's not necessarily going back that way, right? We've seen here for the Arrhenius, there was no acid. But we do see for Bronsted-Lowry that the H2O was an acid, and again, likewise for the Lewis. Okay, any questions about that? Now, again, we're going to focus on this Bronsted-Lowry concept where we have a proton being donated and accepted. We will talk a bit about Lewis acids, a little bit more, but not a lot. But again, for those of you going to organic chemistry, most of organic chemistry really is Lewis acid-based chemistry. Do your homework, okay? For those of you going to organic, I've made up a bunch of homework problems that address organic chemical reactions and the Lewis acid-based chemistry that occurs. Okay, that'll be an advantage going into it. Okay, let's try another. It wants us to name the 6 strong acids and bases and give their chemical formulas. So, Kaylee, what are my 6 strong acids? Again, these are the tables that you must know. This is stuff that you should have known already from Chem 110. What are my 6 strong acids?
It would be, I know it doesn't it have like there's lithium and so LINAK.
Those are the bases.
Oh, okay.
Keenan, what are my 6 strong bases? Keenan, what are my 6 strong bases?
Can you hear me?
I can hear you now.
Oh, there we go. Sorry.
That's okay.
You said 6 strong bases?
Yep.
LiOH, NaOH.
I'm sorry, 6 strong acids. Now I'm saying bases. 6 strong acids. 6 strong acids.
HClO4.
Okay, perchloric.
Your H2SO4.
Sulfuric.
HBr.
Okay. Hydrobromic.
HCl.
Hydrochloric.
HNO3, and I'm missing the simplest one.
Nitric.
H.
So you have 3 binary acids, right?
Yeah, is it HI?
Yeah, right. It's the
Okay.
3 middle nonmetals, and those are your 3 strong binary acids. The other ones are all oxo acids. You just kind of got to know them. But it's the 3
Yeah.
middle halogens are your binary acids, and then there's the perchloric acid, sulfuric acid. Again, only the first H. Okay, so if I were to write sulfuric acid, so this is what it would look like in the molecular equation. How do I know if an acid's aqueous or not?
Well, all acids are aqueous.
Exactly. All acids are aqueous. So when we go from the molecular equation, right? So when we go from a molecular equation to the complete ionic equation, so we only dissociate strong electrolytes. Is sulfuric acid a strong electrolyte? Kaylee? Is it a strong electrolyte?
Yeah.
Yeah, right? That's what the strong means for the 6 strong acids. How do you know when an acid's a strong acid? Anybody? How do you know when
One
it's
of the 6 strong acids, it's a strong acid. If it's
exactly?
not, it's not.
And if it's not on this list, it's a weak acid. It's that simple. Okay? So that's why you got to know your 6 strong acids. If it's not a strong acid, it's a weak acid. Now, are there exceptions to that? Of course, there's exceptions to everything in chemistry. We're not going to worry about that. Okay, so it's a strong electrolyte. But the point here is that we're going to show it like this because the second H, this is still acidic, the second H is weak. So the first one will dissociate, but the second one is going to be weak. Only some of it actually dissociates, a very small amount. Okay. So the other ones, of course, are just have a single H and they are strong, so they would completely dissociate. Okay, any questions about that? Whoops. Okay, Kaylee, how about the 6 strong bases?
NaOH, LiOH, KOH, and then CaOH2, SROH2, and BaOH2.
Exactly right. So looking at the periodic table, starting with the first metal, lithium, which has a +1 charge since it's in group 1. So it's going to be lithium hydroxide, and then we're going to go straight down. So lithium, sodium, potassium. So lithium, sodium hydroxide, potassium hydroxide. Then at potassium hydroxide, simply move over 1 to the next group. That brings us to calcium. Now calcium's in group 2, so it has a +2 charge. So it's going to be CaOH2. And then we're going to go down. So then strontium hydroxide and barium hydroxide. So strontium hydroxide and barium hydroxide. Okay. What phase label would I give these strong bases? What phase label would I give these strong bases?
Aqueous.
They're aqueous, right? So again, we know from the solubility rules, most hydroxides are insoluble with the exception of our 6 strong bases. Okay, now it says group 1 in these 3 guys, but again, the other ones are rubidium, cesium, and francium, and quite frankly, I doubt that anybody is ever going to work with any of those ions. I worked with cesium hydroxide only because I worked at the Hanford nuclear site at the out in Washington State, and so that's the only time you really deal with cesium is if you're working with some type of nuclear decay. Okay, but otherwise you're never going to get these. So we're just going to keep it simple, and we're simply going to say that the exceptions to the rule number 8, that the hydroxides are insoluble, the exceptions being our 6 strong bases. Okay, but again, know that there are exceptions. Thallium hydroxide, for example, is actually a strong base. You don't need to know that. Okay, just these 6 are our strong bases. So any other hydroxide is going to get a phase label of what? Michael, what do you think? Okay, well, again, I can't stress more that this is built on Chem 110. And if you don't know Chem 110, you're going to have to study even more than that 15 to 30 hours a week to go back and relearn your Chem 110. And according to the solubility rules, again, rule number 8 says that the hydroxides are insoluble for the most part, the exceptions being our 6 strong bases, which will be aqueous. But otherwise, if we have an insoluble salt or hydroxide base, it's going to be a solid. So we'll give it a phase label of S. Okay, and that'll be a weak electrolyte. More importantly, it will not be a strong electrolyte. Okay. Okay, so that brings us then to being able to write. You're going to need to be able to write the complete ionic, net ionic, and molecular complete ionic and net ionic equations, because most of the times we're going to work from the net ionic equation. So you got to be able to get there. So again, this is all Chem 110 review, what I've been doing. Okay, this is Chem 110 right here. So for example, what is the formula of hypobromous acid? Again, I stressed, if you had me for Chem 110, you heard me stress over and over and over again the importance of being able to name compounds. If you can name compounds, this course is not going to be that bad. If you can't name compounds, this is going to be tough. So what is the formula for hypobromous acid? So again, very quickly to review how to name acids. Basically, an acid, you have an anion, whatever that is. It could be, you know, it could be a chloride, or it could be an oxygen-containing polyatomic ion. But all of these anions end in one of three things. They either end in IDE, chloride, cyanide, sulfide, oxide. They all end in IDE. If it is an oxygen-containing polyatomic ion, and again, this charge, who knows what this charge is? Who knows what this charge is? 1, 2, 3, -1, -2, -3, same thing here. And then it's going to have a certain amount, well, I'm just going to put Q in, and then it's going to have a certain amount of oxygens, which again, that's going to end in either ATE or ITE. Where the one that ends in ITE, we simply have one less oxygen than there is in the one that is ATE, and their charges are going to be the same as long as this is the same. Okay? Now, I'm not going to go over naming compounds. You need to learn how to name your compounds. If you have issues with it, let me know. So again, if I have this hypobromous acid, well, if it ended in IDE, we would have simply put hydro in front of it, used the stem name of whatever it is, and I'll explain what that is here in a second, and then we would have ended it in IC and added the word acid. If it ended in ATE, we would simply use the stem name, replace the ATE with IC, and add the word acid. And if it ended in ITE, well, we would simply replace the ITE with OUS and add the word acid. Now, just remember, for sulfur, not only did we use the stem, but we added the UR back. And for phosphorus, not only did we use the stem, but we added OR back. So in the case of hypobromous acid, I could see that it ends in OUS, OUS. So that means that it must have been, now notice this is hypo, not hydro. So this is hypo bro, and again, since it was IUS, it must be ITE, so it must have been hypobromite. So again, this is why you've got to know your polyatomic ions. Okay, I'll tell you what, I'm just going to go over it real quick because again, this is going to be really important and you got to be able to do this stuff. So let me just review naming compounds real quick and understanding your polyatomic ions. So again, you have a table that you are supposed to know. It's not a request, it is a must. If I can find them. So this is basically the table that you're going to find that you need to know. It might be slightly different than this. As ions become obsolete, I've removed them. As they become more significant, I add them. But these are the most common ions that are used in chemistry, biology, and engineering. Okay? And you got to know these ions. So, of course, when you're looking at the periodic table itself, we have, again, we have the group 7s. These always make anions, right? They always gain electrons, so it would be the group number -8. So these are always -1. These guys are always going to be -2. It's group number -8. So these are -2. Group number -8. So these are always -3. Carbon, when it forms an ion, which it rarely does, would be -4. Okay. The metals, on the other hand, always lose electrons. So the main group, group 1, they always lose a single oxygen to form +1. Group 2 always lose 2 electrons to form +2. Aluminum always loses 3 electrons to form +3. Boron never forms ionic compounds. Okay. Now, the other heavy main group elements like gallium, indium, thallium, they have 2 possible charge states, +1 and +3. I'm not going to go over why. You could review your Chem 110 to understand why they form those 2. These guys, tin and lead, form 2 as well. They're going to be +2 and +4, and bismuth is going to form +5 and +3. The transition metals, that's these guys here, they can have a whole bunch of different oxidation states, and there's no way to predict them like we were able to predict the main group metals. Okay, and I'm not asking you to memorize them. We can get them out of the name or the formula, since when we name ionic compounds, and I'm talking about naming just ionic compounds, you can go back and learn how to name molecular compounds on your own. So molecular compounds contain only nonmetal atoms and no polyatomic ions. Ionic compounds contain a metal and a nonmetal, or a polyatomic ion and either a metal or some other nonmetal, but a polyatomic ion. So again, a metal and a nonmetal, or it contains a polyatomic ion. So those are ionic compounds. So when naming ionic compounds, we're always going to name the cation, the positively charged species, followed by the anion, the negatively charged species. And we're going to play that they got to be neutral. So for example, if I have, let's say I have aluminum, which again, we can see that aluminum is in a main group 3, so it's going to have a charge of 3+. And if it forms a compound with, let's say, sulfur, and I can see sulfur's in group 6, so it's going to be 2-. We need a neutral compound, so I need a number of these ions and a number of these ions, so that when we add all the charges together, they're 0. We could play the game where we can go this way and just change. So we could say Al2 and then S3. And basically what that means is we have 2 of the +3, and we have 3 of the -2. And when we add these together, we got +6 and -6 is going to be equal to 0. And that's why our ionic compounds are always neutral. Okay. So again, this is a very quick review. This is definitely not a complete review of naming compounds, but this should get you started to make sure that you can do this. Again, this is all Chem 110. Okay, so knowing your polyatomic ions. So I give you this list. And again, like I said, we have the sulfate and sulfite. So here's the sulfate. It's SO4 2-. The ite simply has 1 less oxygen. Now, ite does not mean 3 oxygens, and 8 does not mean 4. If you look at nitrate, it has 3 oxygens and a -1 charges, where the sulfate had 4. So that's why I gave you a limited number to remember, and then I'm going to show you how you can figure out the rest. Okay. So again, just put these things on little index cards, put the formula on one side, the name on the other. Any little free time you have, just do it a few minutes, and I guarantee you will learn these things very, very quickly. It's not hard, but you have to try, you have to do it. Okay. Okay, so now, what about the charges? So you have to memorize the number of oxygen. Just for the 8s, that's it. You need to know 1. That's 1. So really, you don't need to memorize this because you know ite simply means there's 1 less oxygen than 8. So you need to know how many oxygen sulfur will have. Now, what's nice about that, you now know how many oxygens the other elements in that same group are going to have. Okay, you're going to know how many in the same group. So, for example, selenium is also in group 6. So, selenate is going to be SeO4 2-. So once you know 1 oxoanion, and I'm talking just 1, you know how to name all the oxoanions in those groups. There are 2 exceptions. I'll talk about them at the end. Okay? What about the charge? Well, sulfur is in group 6. 6 minus 8 is -2, just like sulfide, right? Sulfide. So sulfide ends in IDE is simply S2-. Sulfate, the only one I needed to memorize was SO4 2-, same charge. Because I know sulfate, I know that sulfite is simply 1 less than that 4, so sulfite is SO3 2-. Okay, now, so that's going to be true for all the other ones as well. So, for example, let's look at the other one that I asked you to know, which was the chlorate. Okay, so chlorate is ClO3, and it's minus, just like chloride. Cl-, right? Chloride, group 7, has a -1 charge. So this is chlorate. So I know that 1 less is going to be my chlorite. But with the halogens, group 7, the halogens, we actually can have 4 different oxygen-containing anions. We could actually have less than 2. We could have ClO-. We're going to still call it chlorite, but we're going to put the prefix hypo. Chlorite. We could actually have 1 more than the chlorate. We could have ClO4-. Notice that the charges are all the same as the monatomic ion. So this is a monatomic ion, 1 atom, monatomic, ion being the charge. So this is a monatomic ion. These are polyatomic ions. Polyatomic meaning it has more than 1 atom, and ion again meaning it has a charge. Now, if it has more than 1 more oxygen than 8, we're still going to call it chlorate, but we're going to add the prefix per to it. So it's perchlorate. Okay, so all you needed to know was this and the rules for the other ones. Ite's 1 less than 8. If you have 2 less than 8, then it's hypoite. If you have 1 more than 8, then it's going to be the perchlorate. Now you know how to name all the oxoanions for group 7s. Right? So for example, let's say I take Br and I have BrO4-. What's the name of BrO4-?
Perbromate?
Yeah, right. It's 4, so it must be per, and this is bromium, so the stem is brom, B-R-O-M. We dropped the 8, and I'm sorry, we didn't. We're not going to the acid yet. So it's just going to be perbromate, right? So this is perbromate. What's the formula for hypoiodite? What's the formula for hypoiodite?
IO-.
Say again? IO minus. Yep, IO minus. So once you know how to name one, you know how to name them all in a group. Now I said there's two exceptions. Those two exceptions are carbonate. So carbonate, which is CO3, you would think has a charge of -4, but it doesn't. It only has a charge of -2. So you have to memorize that one separately. The other one is nitrate. Nitrate, being in group 5, you would think has a charge of -3, but it doesn't. It has a charge of -1. So that's the other exception. Now, when we get lower, like phosphate or arsenate, well, they're going to follow it again. So again, the phosphide, being in group 5, would have a 3- charge. The phosphate, which you have to remember what the 8 is actually, again, 3-, and it has 4 oxygens in this case. So phosphite would be PO3, 3-. Arsenate is going to be ASO4, 3-, just like the phosphate. So I'm asking you to memorize this one, and then you could name all of the arsenates. Okay, so again, these are the only two exceptions where the charge doesn't match the monatomic ion. Again, this monatomic ion would be 4-, and this monatomic ion would be 3-. So they don't match. Those are the only two. Okay, any questions about that so far? Okay, now with that quick review, let's do this. So what is the formula then for hypobromous acid?
Is it HBRO?
Yeah, right. Again, the hypo, meaning it's in the us, indicate that it is much less. So that is going to be the hypobromite, right? And hypobromite has the formula of BRO, and then it's -1, right? Again, since it is in group 7, it's going to have a -1 charge. And to make that an acid, we simply added H pluses, right? So now we have BRO minus, and we simply add enough H pluses until we have a neutral compound. So how many H pluses do I have to add? Just 1, right? Since that is a -1 charge, that's a +1 charge. Our hypobromous acid has the formula of HBRO. Okay. What's the phase label of hypobromous acid?
Aqueous?
Aqueous. Why is it aqueous?
Because it's not going to be it's not a liquid. I know. I don't know why it's aqueous, but I do know it's not going to be a
Okay.
liquid at all.
Here's the only reason. It's an acid. All acids are aqueous.
Okay.
Are there exceptions to this? Yes. Again, there's exceptions to everything. But almost all acids, you put them in water and they dissolve. Okay. So is it soluble?
Yes.
Yes, exactly what soluble means is that it dissolves in water. It's aqueous. So soluble means aqueous. Is this a strong or weak electrolyte?
Would it be weak electrolyte?
Why?
Because it's not a strong acid?
Exactly, right? That comes to this column here. So sometimes you don't always answer these in order. Sometimes you have to answer them out of order to get the other ones. So yeah, you just told me that it is a weak acid, and that weak in weak acid means it's a weak electrolyte. Okay, so it's going to look like this in the molecular equation, HBRO and then phase label aqueous. What's it going to look like in the complete ionic equation? What do we dissociate going from a molecular equation to a complete ionic equation?
I'm not sure.
For any equation, what do we dissociate going from a molecular equation to a complete ionic? Keenan, what is it?
Strong electrolytes.
Strong electrolyte. It's that simple, and that's always the answer. We only dissociate strong electrolytes. Is hypobromous acid a strong electrolyte? No, we just established it's a weak electrolyte. It's a weak acid. So it's going to not dissociate. We're just going to show it just like it was in the molecular equation. And no matter what, the phase label always follows. Okay. Okay, ammonium chloride. What's the formula for ammonium chloride?
Would it be NH4Cl?
Yeah, right. Okay, so again, when you're doing this, the first thing you ask yourself, is this thing ionic or molecular? Well, again, since you know your polyatomic ions, and again, is that list that I give you all the polyatomic ions that exist? No, it's not. But we're going to pretend like that is the only ones on that list, and the other ones like the oxo anions that I showed you how to name. Otherwise, we're going to assume that those polyatomic ions don't exist. Again, there are more, and we're going to see more as we go throughout the course. But if you recognize the ones that are on the list, again, these are the most common, the ones you're going to find all the time. Unless you're in organic chemistry, then you're going to see a lot of other weird organic compounds. But the ammonium ion, I already recognize as NH4+. So I know this compound is ionic. And chloride, well, that's just a monatomic ion. And so we got a +1 and a -1, so the formula is just going to be NH4Cl. Okay, Katrin, is this, what phase label am I going to give ammonium chloride? What do you have to, let me ask this, what do you have to think about, know, to determine whether or not this thing is going to be soluble or not? So this is where we go through. This is, again, why you got to know how to name compounds. First question you ask yourself when you name a compound, is it ionic or molecular? We established it's ionic since it contains polyatomic ions. Then we need to know what type it is. Is it an acid? Is this an acid? No, right? We would generally expect the H to be out front. As we progress, we're not always going to put the H out front anymore. We're going to find out that we can determine whether or not it's an acid if it has an acid equilibrium constant. We'll just look up the Ka values. If it has a Ka value, and it's not, strong acids won't have Ka values, but you already memorized them as strong acids. Weak acids are going to have Ka values. So you'll be able to look it up and go, oh, it has a Ka value. That compound must be an acid. But so no, for right now, we don't see any H's out front. So it's not an acid. We know that all acids are aqueous. They're soluble. Okay, is it a hydroxide? So that's the second type, right? Acids, then hydroxides. Not a hydroxide, there's no OHs there. And we know that the hydroxides, whether they're soluble or insoluble in their phase labels, dependent on the solubility rules, rule number 8, which tells us that most hydroxides are insoluble. They'd get a phase label of S. The exception being the 6 strong acids. They would be soluble and would get a phase label of aqueous. Then we have the metal oxides. I'm not asking you to know much about the metal oxides, but to recognize them. Well, that would be just a metal and oxygen, no other nonmetals. You can have a bunch of different metals, but only oxygen is the only nonmetal. So metal and oxygen. Well, this doesn't contain either, so it's definitely not a metal oxide. Therefore, it is what? It is a salt. And for that, we need to use the solubility rules. So if we have a salt and it contains the ammonium ion, do we have any rules for that?
Yes, we do.
Yeah, it's rule number 1. Again, I don't expect you to know these in order, but you should learn rule number 1 and rule number 2 of the solubility rules because there's no exceptions to them. And rule number 1 of the solubility rule says that any salt that contains the group 1A metals, lithium, sodium, potassium, rubidium, cesium, or the polyatomic ion, the ammonium ion, is soluble without exception. So the solubility rules tells us that ammonium chloride is soluble. Therefore, what phase label does it get?
Aqueous.
Because that's what soluble means, aqueous. Okay. Now, can you tell me, well, we've already addressed this one, right?
Yeah.
We said it was a salt. So is this salt a weak or strong electrolyte?
It's strong because it's soluble in water.
Okay, it is strong, and this is important, Because it's a soluble salt. Soluble does not mean strong. All acids are soluble. All acids get a phase label of AQ, but in this case, it's a weak acid. It did not dissociate. It only dissociates a tiny bit. So how am I going to write ammonium chloride then, going from the molecular equation where it would look like this with the phase label AQ to the complete ionic equation? Will it dissociate?
Yes. So it'll
Yes.
be NH4 plus Cl minus.
Exactly, right? Yes, because strong electrolytes dissociate. So this is going to be NH4 plus aqueous plus Cl minus aqueous. Okay? Again, if you have questions, let me know. Okay, let's try the next one. Iron 2 hydroxide. Eugenie, what is the formula for iron 2 hydroxide? Is it ionic or molecular?
Ionic.
Yeah, right. We have a metal and a polyatomic ion. So what is the charge on the iron?
2 plus.
Yeah, right. That's what the Roman numeral is. That's why I said for transition metals and the other heavy main group metals. So I'm talking about gallium and tin and indium and thallium, lead, bismuth. We're always going to put a Roman numeral to indicate the charge. Now, we don't put Roman numerals for the group 1A metals because they're always +1. We don't put any Roman numerals for the group 2A metals because they're always +2. And we don't put a Roman numeral for aluminum because it's always +3. But there will be Roman numerals for all of the transition metals and the heavy main group metals. Okay, so yeah, it's iron +2. Well, what's the charge on hydroxide ion? What is hydroxide ion?
A base.
What's its chemical formula? It is a base, I agree. Hydroxides are bases.
OH minus.
Okay, so what's the formula then for iron 2 hydroxide?
FeOH2.
Yeah, and in OH being in parentheses. If there's only one, you don't need parentheses. Only if there's more than one will you need parentheses around your polyatomic ion. You never put parentheses around a monatomic ion. Now, we're going to find out later on, I'm going to kind of violate some of that when we talk about complex ions in the last chapter. We'll worry about that. You'll understand why when we get there. We're going to put parentheses around things. It's part of the naming system. And that's why you don't put parentheses around it. Otherwise, you're indicating it is something totally different, which again, we'll talk about once we get to naming complex ions in the last chapter that we cover. Okay, so what phase label am I going to give, or actually, if you want, answer any of these questions. So Eugenie, what other questions could you answer here? You already answered one of them for me, partially anyway.
I could answer if it's a base.
Yeah, you told me is the base. Is it a weak or a strong base?
It's a weak base
Why is it a weak base?
because it's not on the strong base.
Perfect, right? That's exactly right. So it's a weak base because it's not one of your 6 strong bases. Could you tell me phase label, or if it's soluble or insoluble? Is it a weak or strong electrolyte?
It's a weak
Yep, that's
electrolyte.
what weak means. So it's a weak electrolyte. Okay, now what about the phase label and solubility?
It's
Okay, I want to address this idea of time on the exam. Part of the reason you don't have time on the exam is because you didn't do as I asked. I asked you to memorize those tables. I gave you plenty of time before this class even started, weeks before this class started, to do that. Okay, if you hadn't had Chem 110, or you're wherever you happen to have Chem 110, because in the summertime, that is an issue. We have a lot of students who don't take our Chem 110. We expect a lot out of our Chem 1 student, 10-1 students. So you might not have had that wherever you're coming from. But I gave you plenty of time and plenty of warning to tell you that you're going to need to know this stuff. So if every time you need to look up in the table whether this is soluble or insoluble, yeah, you're not going to have enough time to take an exam. I agree with you. But again, that's on you. You were supposed to know your solubility rules. You are expected to know your solubility rules. So you would know, according to rule number 8, that hydroxides are generally insoluble with the exception of the 6 strong bases. Insoluble, when we're talking about our salts, means it has a phase label of solid. Okay, so we're gonna show iron 2 hydroxide is being dissociated in the complete ionic equation. Yes or no? We're gonna show it as being dissociated. No,
No.
why not?
Because
It's a weak electrolyte. We only dissociate strong electrolytes, so no. So we're not. It's going to look exactly the way it did in the molecular equation, and we're going to give it a phase label of a solid. Okay? Okay, so next, can anybody tell me what this is?
That acetic acid.
That is acetic acid, right? So again, a polyatomic ion that you must know. C2H3O2 is the acetate anion, right? So that's acetate. It ends in ATE. We're going to replace the ATE with simply IC and add the word acid. So this is acetic acid. Okay. What phase am I going to give acetic acid?
Aqueous.
Aqueous, because all acids are. AQ. That's an A, believe it or not. And so is it going to be soluble or insoluble?
Soluble.
And that's exactly what aqueous means, soluble. What else can you tell me about it?
It's going to be a weak electrolyte
And why is it a weak electrolyte?
because it's not one of, because it's a weak acid, because it's not one of the
Exactly.
strong acids.
Exactly, right? So we know it's an acid, it's acetic acid, it's got that H out front, and you're right, it's a weak acid because it's not one of the 6 strong acids that you must know. Okay, so what is it going to look like then in the complete ionic equation? This is what it looks like in a molecular equation, right? In a molecular, there's no ions in a molecular equation. They're all neutral molecules. So what's this going to look like in my complete ionic equation?
Well, it's not going to dissociate, right?
That's correct. We only dissociate strong electrolytes. So it just looks like that. And it had a phase label of aqueous, so it'll continue to have it. So no, we only dissociate strong electrolytes. Okay. Okay, now this one would be you'd truly impress me if you could name this. You know more than you would have learned in Chem 110 here. However, some folks who've had really good chemistry courses in high school are actually able to name this. Okay, so what we're going to have here is we're going to have, this is the conjugate acid of a base. So like I said, we're going to have neutral nitrogen-containing molecules. So in this case, it was actually N2H4, and that is what we called hydrazine, okay? So this neutral molecule is called hydrazine. And when it accepts a proton, right? So it accepts a proton in an acid-base reaction, and it forms this polyatomic ion. So now you're going to be able to recognize more polyatomic ions, but you're going to have to recognize that in the full context of the chemical reaction. This would have been some acid reacting with a base. So you would have known that this was an acid-base reaction to form this new ion. And this hydrazine, okay, the INE becomes IUM. I do not expect you to name these, by the way. I do not. We're going to do no more naming than you actually should have learned in Chem 110. But just to give you an idea of if you do know this, it's going to, again, make things easier to understand. So I could see then from the context of the reaction, again, I'm not asking you to just recognize that. You would have recognized it from the whole chemical reaction. I would have told you that this was hydrazine. I would have told you that this would have been the hydrazinium. Okay, so since we're going to replace that, it becomes hydrazinium. So hydrazinium. And then what's the rest of it? What's the charge on this ion? So if this is a polyatomic ion, what's the charge on this ion? You make
-1.
Yeah, right. It's just bromide. It's just group 7, right? So it's just group 7. It's bromide. So it's just a -1. Okay. So that gives us our NHBr. And what do we call that when we're naming it?
Is it just bromide?
Yeah, it's just bromide, right? It's a monatomic ion. So it's the stem and we end it in IDE. So it's just bromide. So this is hydrazinium bromide. Now, what else can you tell me about it? Is it ionic or molecular? You're overthinking this stuff. This stuff really isn't hard. It really, really isn't. You're just overthinking it. Is it ionic or molecular?
Molecular?
Anybody disagree?
I'm sure.
What is ionic compounds composed of?
It's ionic because it's a polyatomic ion.
They're ions, right? So this thing must be ionic.
I wasn't thinking there.
That's okay. So if it's ionic, let's jump to this one here. Is it an acid, a base, a metal oxide, or is it a salt? Is it an acid?
Yeah, because it's the conjugate base, correct? Is that what you said?
I would agree with you there, but a conjugate isn't considered to be an acid or a base initially. It became an acid or became a base, so it wouldn't be named as an acid or a base. So for example, this hydrazine, that's actually a molecular compound, and we would call that a base. Okay?
Okay.
But it's a molecular compound, so it gets real complicated in this table, but that's why we're not going to worry about that kind of stuff. That's a molecular compound. Molecular compounds are not strong electrolytes, so would never show them as being dissociated. That's what you need to know. What you also need to know is that all neutral nitrogen-containing compounds, because they probably have all the same properties of water, right? They're going to have dispersion forces, of course, or London forces. They're generally polar because they have the nitrogen super electronegative, and the other elements connected to it probably have a different electronegativity. So they're most likely polar, so they're going to have dipole-dipole interactions just like water. And then we have the nitrogen that's almost, that has the connected to the hydrogen. Well, that's the electronegative nitrogen, oxygen, or fluorine with a lone pair that's directly connected to a hydrogen. That means it also has hydrogen bonding. So generally, nitrogen-containing molecules have exactly the same intermolecular forces as water does, and therefore they easily dissolve in water. Okay? So that's why they're always aqueous. They're molecular, so they're definitely not, they'll always not be dissociated, going to the complete ionic, but that's why they're always aqueous. They have the same intermolecular forces as water. Like dissolves like. Okay, so it's not an acid. Is it a hydroxide base? No, right? There's no hydroxides. Is it a metal oxide? It doesn't contain metal or oxygen, so definitely not. Therefore, it's a salt. Okay? So it's a salt. So to be able to determine whether it's weak or not, I need to know if it's a salt, whether it's soluble or insoluble. Is this thing soluble or insoluble? Do we have any roles for the hydronium ion? No, right? There's nothing weird like that in the the rules. Do we have any rules for bromide? Yeah, according to rule number 3 of your solubility rules, any salt that contains the bromide, chloride, or iodide ion are generally soluble with the exception of silver, mercury, and lead. Well, this is not silver, mercury, or lead, so that means this bromide salt is soluble, which of course means it's aqueous. And so is this salt a strong or weak electrolyte?
Strong.
Yeah, soluble salts. That's the only time soluble and strong electrolyte go together is when you are talking about salts. So soluble salts are strong electrolytes. So are we going to dissociate it?
Yeah.
Absolutely, because that's what we dissociate. We dissociate strong electrolytes, right? We dissociate strong electrolytes. So it's going to dissociate into its individual ions, which we've already established as the hydrogenium ion and the bromide ion. Now I'm just going to go through these because I've spent way too long on this already. Okay, so NO2 and NO3, right? Now NO3 is the only one I memorized, and I know that that's nitrous acid. Well, I know that NO3 is the nitrate, right? So I know that NO3 minus is nitrate. We're going to replace the ATE since it's got H's out front, right? And it's now neutral. So to be an acid, to be called an acid, it has to be your anion and then enough H's to make that anion neutral. Otherwise, it's not called an acid, okay? So this is NO3, which has a 1- charge, and of course the H has a +1 charge, so there's our neutral acid. And it ended in ATE, so we're going to replace the ATE with IC, so this is called nitric acid. We know that all acids are soluble. Nitric acid is a strong acid, one of the 6 strong acids we need to know. And of course, that strong acid means that this thing is a strong electrolyte, and we dissociate strong electrolytes. And then we have this guy here. Well, that's 1 less oxygen than my 8, so I know that this is nitrite. And if it ends in ITE, and again, we have the H, which makes it a neutral compound, therefore it's an acid, right? We gave enough H pluses to make that neutral. And if it ended ITE, we simply replace the ITE with OUS. So this was called nitrous acid. Again, all acids are soluble, so we get a phase label of aqueous. And this time I know that nitrous acid is a weak acid because it's not one of the 6 strong acids. Weak acids are weak electrolytes, and we don't dissociate weak electrolytes. So it's going to come straight down and be undissociated. Okay, any questions with any of that good stuff? Again, this is all Chem 110 stuff. The only thing new that I discussed was that. Okay, as a continuation of Chem, no, this is not Chem 110, this is Chem 112. So it simply says for the following reaction, it wants you to label what species are acids and bases and the acid conjugate base pairs. So so what would you consider this reaction? And you got to recognize what it is too. So do you recognize it's an acid-base reaction? And if so, how? I mean, the question certainly implies that it is, but if I didn't even give you this, you should be able to identify this as an acid-base reaction. And the question is how and why?
The HF donates H plus to the OH to form. Oh wait, no, it does. Yeah, it does to form the H2O2.
Yeah, I don't know how I missed the H, but that's the H coming over there. Okay. So yeah, I have a proton transfer reaction. So by the Bronsted-Lowry definition, again, the one we're really going to use, yeah, I have a proton transfer reaction. So this must be an acid-base reaction. So what is my acid then? What is my acid?
The HF.
The HF. And my base?
The OH2 yeah, is that minus.
Yeah, the
Okay.
here it was the so again the acid is the H plus, the proton donor, and the base is the H plus or proton acceptor, right? So this was the donor, this was the acceptor. Okay. Can you identify any other acids or bases in this reaction? Well, let me ask you this. Can you identify any acid-base conjugate pairs? Let me go one step further. What's the difference between an acid and a base, an acid and a base in an acid-base conjugate pair? What is the difference between the acid and the base in an acid-base conjugate pair?
The acid has another hydrogen.
Yeah, H plus. The acid has one more H plus than the base does. So can you identify any acid-base conjugate pairs?
So would the H2O2 and the OH2 minus be the conjugate or the acid-base conjugate pair?
Yeah.
Or no?
So therefore, this would be classified as what?
That be considered an acid then, since the
Yeah,
OH2.
right? So if that's the base, this must be the acid. Are there any other acid-base conjugate pairs? Katrin, what is it?
HF and F minus would be the conjugate base.
Yeah, right. There's another conjugate pair. And this would be the base. Okay, does that make sense? Okay, so that's it. Oops, I keep trying to admit her and she can't get her in. There we go. Okay. Okay, so now we're back to Chem 110. So this is just what you would have learned in Chem 110. It wants you to write the complete the following reactions by writing the molecular complete ionic and net ionic equations with phase labels for each of the reactants. And we know that these are acid-base reactions, so I want to know what salt is formed, right? Because by definition, an acid-base reaction forms a salt. In fact, the definition of a salt is the product of an acid-base neutralization reaction, okay? So again, acid-base reactions are always going to form salt. So let's start with the molecular equation. So what is the formula for aqueous hydrogen cyanide? So what's the formula for hydrogen cyanide?
HCN.
Yeah, right. Again, CN is a polyatomic ion that you must know, right? That's the cyanide ion. And if it's an acid, hydrogen cyanide, so that'd be H plus. Because it's aqueous, we know that it's an acid. And what would we call this acid then? And acids are always soluble, so it's aqueous. So what are we going to call this acid? Again, we know the name of this, that is cyanide. So we're going to replace the IDE With IC, add the prefix hydro, because when it ends in IDE, you add hydro and then ic, and then we put the word acid, so that would be called hydrocyanic acid. The hydrocyanic acid is reacting with ammonia. What's the formula for ammonia? What is the formula for ammonia? So again, ammonia is the only, in Chem 110, ammonia was the only non-hydroxide weak base that you should have known.
It's NH4.
That's ammonium. What is ammonia?
NH3.
NH3. Okay, so there's ammonia. And what phase label do we give ammonia?
Aqueous.
Yeah, again, I just talked about that, right? I said for these nitrogen-containing molecules, they have the same intermolecular forces generally. I mean, not all of them, of course, but generally, we're just going to assume that they do, just to make life easier. They have the same intermolecular forces as water, therefore they're going to dissolve in water. Okay, so now, what's going to happen here? So now we got to recognize this is an acid and this is a base, right? So we recognize this. This is an acid, this is a base. What happens with an acid-base reaction? Again, we're always working from the Bronsted-Lowry definition.
Is it, will the H from the HCN go to the H3 to form ammonium?
Yeah. So what happened here is that the H plus left. So that's going to leave us with Cn minus. That's going to leave us with Cn minus. And then this became, we added an H, so NH4, but it's it's plus, so it's going to be NH plus. So what do I write over here? NH4 plus Cn minus? It's a molecular equation. There are no ions in the molecular equation. So we're going to write the salt that was formed, NH4, and then that's my plus 1, and then a minus 1, so Cn. That's the salt, right? So that was the salt that was formed. What phase label do I give that salt?
Aqueous.
Yeah, according to rule number 1, any salt that contains the group 1A metals or ammonium is going to be soluble without exception. So it's going to be aqueous. Okay. Any questions about that? Now, I will say that sometimes you cannot identify conjugate acid-base pairs from the molecular equation, right? Because I know that the conjugate of the hydrocyanic acid is actually the cyanide ion, and the conjugate of ammonia is the ammonium ion. So sometimes you have to go to the complete ionic equation to determine what the conjugate acid-base pairs are. Okay, so now let's go to the complete ionic equation. Will I dissociate hydrocyanic acid? What do we dissociate going from a molecular equation to a complete ionic equation? You should all be able to tell me immediately.
Strong electrolytes.
Strong electrolytes. Okay, it's simple. Don't make it hard. What do we dissociate going from molecular to complete ionic? We only dissociate strong electrolytes. Is hydrocyanic acid a strong electrolyte?
No,
Why not?
because it's not on the strong acids.
Therefore,
base.
it is a weak acid and thus a weak electrolyte. So we're going to bring it straight. Is this balanced, by the way? Forgot that step. Yeah, it's already balanced, right? So again, I can see there's the one cyanide, then we had the NH3 and the 1H, which would be the NH4, so it is balanced. Okay, you could also count the atoms if you want to do that. That actually takes longer. Okay, so we're not going to dissociate. This is a weak electrolyte, so we'll bring it straight down. Is ammonia a strong electrolyte?
No.
No, again, it's not one of our 6 strong bases. And we know that neutral nitrogen-containing molecules are always going to be weak bases. We don't associate weak electrolytes, so that is NH3AQ. What about the ammonium cyanide? Is that a strong electrolyte?
Yes.
Yes, again, it is a soluble salt. The only time aqueous means strong is when we are talking about salts. So this is a soluble salt, so it's a strong electrolyte, and it's going to dissociate into its individual ions. And that's what we will write. Okay. Okay, so there it is. Now, if this was balanced and you split them up and brought them down correctly, this should already be balanced. If this isn't balanced compared to that, there's a mistake somewhere. Okay. Okay, any questions with writing complete ionic equations? So this is the way it really looks. I had a beaker of hydrocyanic acid where the majority of the hydrocyanic acid was intact as these neutral molecules, still floating around, but they were intact. The other beaker had a solution of ammonia. Some of it actually reacted to form ammonium hydroxide. We'll get into that later. But most of it just remains intact as neutral NH3 molecules floating around. When we combined them two, we formed it was an acid-base neutralization reaction, and we formed this salt, ammonium cyanide. But ammonium cyanide in the beaker that it's in is fully dissociated because it is a strong electrolyte. So again, this has really shown us the reality of it. Okay, my net ionic equation. How do I get my net ionic equation from my complete ionic equation? What do I do?
Anything that shows up on both sides gets canceled out.
That's right, right? So are there any, and we call them spectator ions, things that are the same on both. Are there any spectator ions?
No, so it would be the same as the complete ionic.
And I suggest that you would do, if I gave you something like this on an exam, and the net ionic equation was the same as the complete, I would say same as above. That way you're not rewriting this and taking any chances of just making simple errors, okay? And again, saving yourself a tremendous amount of time. Okay, so this is what we would consider to be an acid-base neutralization reaction. Again, we learned about basically 5 different types of reactions in Chem 110. No reaction at all, which is actually an important reaction a lot of times when you don't want to die. We talked about precipitation reactions. We talked about acid-base neutralization reactions. We talked about acid-base reactions with gas formation. And we talked about oxidation reduction reactions, or also called redox reactions. Okay. So this was one of them. This was the acid-base neutralization reaction. We had the acid reacting with the base to form our salt. Okay, let's go to the next one. So this is the same, so I'm just going to go through it. If you have questions, please stop me and ask. Okay, so the molecular equation, well, we have aqueous solutions of calcium carbonate. So calcium is a group 2A metal with +2 charge. The carbonate's a polyatomic ion with a 2- charge. So we have a +2, -2, so that is my neutral salt. I'll come back to the salt part here in a second. Then I have nitric acid. Well, nitric, that means that was nitrate, and nitrate is NO3 -1. To make it an acid, we'll add H pluses till it's neutral. Well, that means we only need to add 1 H, and now we have our neutral. Now, I know all acids are soluble, so I can put an AQ there. Now, for the calcium carbonate, well, I know according to my solubility rules, carbonates are generally insoluble. with the exception of rule number 1. Rule number 1 being those group 1A metals and ammonium. Well, that's not a group 1A metal and it's not ammonium. So this is not an exception. So this means this is insoluble, which means it gets a phase label of a solid. Now, most ionic reactions, if I can't do a transfer of an H, which would be a Bronsted-Lowry type reaction, well, in this case, it really still is. We didn't really learn this in Chem 110, but now that you can start to more fully understand these chemical reactions, we have the H plus going to the oxygen on the carbonate. And in fact, we have that CO3 2 minus, and we have H plus 1, so that means we're actually going to need 2 of them. So when I'm balancing it, I can immediately say, well, there must be 2 of them because I need 2 to form the H2CO3. And then the counterions just, well, that was the cation with the anion. So now we're going to take the cation with that anion. So the calcium is 2 plus since it's a group 2A metal. The nitrate we already know is -1. So that means we have to have 2 -1s to cancel out the +2 of the calcium to give us our neutral. Okay. Now this here, that's carbonic acid. What we learned is that carbonic acid, or salts that react with acids that have carbonates, carbonic acid is unstable and it breaks down into carbon dioxide gas. So that's CO2, which leaves behind H2O, which is water, which is our solvent. So that's liquid. Okay. And again, you were just asked to memorize that salts that contain carbonate, CO3, that reacted with any acid, strong, weak, doesn't matter, any acid, would form carbon dioxide and water and then leave behind whatever salt from the cation and the anion. The cation of the carbonate and the anion of the acid would form our salt. You also learned that sulfites, not sulfates, but sulfites, SO3 2 minus, reacted to form sulfur dioxide and water, and sulfides, when reacted with acid, formed hydrogen sulfide, H2S. We're not going to worry about them. This is going to be the one that we deal with in Chem 112. This is the one that occurs constantly throughout nature, every single day. It occurs in your body, okay? So this is a really important one. And so I do want you to recognize this, that carbonates, when reacted with any kind of an acid, form carbon dioxide and water. They first form a carbonic acid, but that's unstable, and it just immediately breaks down into carbon dioxide and water. Now, calcium nitrate, well, I know it's soluble because according to rule number 2, any salt that contains the acetate, perchlorate, or nitrate anion is soluble without exception. So that is aqueous. And as far as being balanced, I have a calcium, I have 2 nitrates, and then I have, let's see, I have this carbonate. So that's a carbon and 3 oxygen, and then the 2 hydrogens I didn't account for. So there's the 2 hydrogens and the 3 oxygens. Well, there's the 2 hydrogens, the 3 oxygens, and the 1 carbon. So it is balanced. Okay, and again, I kind of balanced it as I went because I knew I was going to need 2 hydrogens to form that carbonic acid. Now, solids, liquids, and gases are never strong electrolytes, so I can simply bring them down. I don't even need to know that this is a weak electrolyte since it's an ionic compound, but it's not a strong electrolyte. That's what I need to know. Nitric acid I do know is a strong electrolyte because that's one of my 6 strong acids, so it's going to form the 2H plus and the 2 nitrates. Then again, I have a soluble, and I know this is a salt. It's ionic. It's a metal and a polyatomic ion. Not an acid, no H's. Not a hydroxide, no OH's. Not a metal oxide because it contains another non-metal rather than just oxygen. Therefore, it's a salt. It's a soluble salt, thus a strong electrolyte. So it's going to dissociate into its individual ions. Again, gases, liquids, not strong electrolytes. In this case, these are both molecular and they're non-electrolytes. Even though we know a very, very small amount of H2O actually ionizes, we still consider it to be molecular. Now, that is our complete ionic equation. Next, we just want to kill off spectator ions. So the only thing I see same on both sides are these two nitrates. The calcium is part of a solid here. It's free floating over here. The acidic hydrogen is now part of water molecule, so they're not the same. So you'd simply bring down what's left, and this gives us the net ionic equation. And again, the net ionic equation is what we're generally going to work from when we're trying to quantify our chemical reactions. Okay. And this would be considered to be an acid-base reaction. It's a neutralization reaction, but we just say acid-base reaction with gas formation. And again, any acid-base reaction forms a salt. And so that is our salt. Okay, any questions with any of that good stuff?